In this exam exercise from 2016, we will model a very relevant example for a microbiologist, which is the movement of a bacterium. This is a difficult task, so let's go through all stages of writing a code again. Let's start with defining the problem. We have a Cartesian space in 2D, so we have a square in which the bacterium can move. The bacteria starts at coordinate x is 0, y is 0. The bacterium is going to move around with a speed of 1 micron per second. After time interval delta t, the bacterium switches direction. This interval delta t is a random number and it can be any value between 0 and 10 seconds. The angle at which the bacterium travels in a new direction is also random. It can be any value between 0 and 360 degrees. Each new position of the bacterium can be calculated with the following two formulas for x and y that are given in the exercise. So now we have all information summed up, we can think of a logic flow to solve the problem. The time span in which the walk of the bacterium will take place is 1,000 seconds. Do we already know how many steps the bacterium will have to take? Or better asked, how many calculations we will have to make? No, we don't, because the delta t is random, so it could be 100 steps, it could be 1,000 steps, or it could be a whole other number of steps. Since the amount of calculations we need to make is unknown, we have to use a while loop. So, until the time reaches 1,000 seconds, or while the time is not 1,000 yet, we should do the following. First, define the value that delta t will have for that particular step. Then, calculate the value that phi will have for that particular step. With this information, we can calculate then the new x and y coordinates of the new position of the bacterium. When this is done, we can plot the path that the bacterium has made as a line between the old and the new position. This means that we should also store the old position, else we cannot plot it. After we did this, we can check if we already passed 1,000 seconds by calculating the new time. If we didn't, we repeat everything. If we did, we can stop and plot the final position. So let's try to put this in MATLAB. Let's open a new script. First of all, clear all your variables. Then define all the variables you already know. X is 0, y is 0, and the initial time is 0. Then the speed is 1. And the maximum time is 10. And then with this data, we can already plot the initial position. And we're going to plot this with the green asterisk. The assignment told us to keep the axes equal. And now we're at it, let's also already add the x labels and y labels. So now we've done that, we can plot it. And there we see that the bacterium indeed starts at x is 0, y is 0. Let's add the while loop to the script now. Let's keep the flow at the side of our screen because we have a lot to do and that might make it easier. So first of all, we have to define while t is smaller than 1,000 seconds. In the core of the while loop, we first have to define the variables, including delta t. This has to be a random number, so we can use the rand command. This command gives a random number between 0 and 1. If we multiply this by 10, or t in this case, we get a random number between 0 and 10. For phi, we can use the randi command. This command returns a random number between 0 and the number you specify. In this case, it's 360. So now we get a random number between 0 and 360. Then we have to store the old x and y. We can just call them xold and xy and give them the value of x and y. Now we have defined all the variables, we are ready to calculate the new x and y of the bacterium, so the new coordinates. And we can do this with the formulas that are given in the exercise. Once we have done this, we can plot a line between the old x and y and the new x and y. And to do this, we can define a vector for x existing of the old x and the new x, and a vector for y existing out of the old y and the new y, and then plot this, and then you get a line between the 2 points. Lastly, we calculate the new value for t, and MATLAB will check whether this t is still under 1000. If this is not the case, then we go out of the while loop and we plot the final position. This position will be plotted with a red circle. Now we have implemented the whole logic flow in our code, so let's see if it works. And we only plotted the final position. But we do see that it's not at 0, 0 anymore, so something happened. What did we do? Oh, we forgot to hold on. So now it will not override. And see, we now plotted the whole path of the bacterium, and we see that it started over there and made this whole path until it ended up at the red circle. The second question of this exercise is a little more challenging. The Cartesian space isn't unlimited anymore, but there's a box inside, and the bacterium is constrained to this box. The box has walls as y is minus 20 and y is 20, x is minus 40 and x is 40, and there's a gap between y is minus 5 and y is 5. Let's start by plotting the box. By defining 2 vectors, one for the x-coordinates of the corners of the box and one for the y-coordinates of the corners of the box, we can plot lines between these points and in that way plot the box in MATLAB. So let's do this in MATLAB. First of all, define the values of the corners of the walls. Then once we've done this, we can construct the vectors that we have previously defined. So these are all the corner points of the walls. And once we've done that, we can plot a line between them. And we want to use a black line. And let's make it a bit thicker, line width 3. And now that we've plotted it, we see that we managed to indeed plot the box, but the bacterium is still able to move freely in and out of the box. If you plot it again, you again see that the bacterium can move anywhere, and that's not what we want. So now let's add the constraints that we need to keep the bacterium in the box. The biggest constraint that we should add here is that as soon as the bacterium runs into a wall, it should bounce back. This bouncing behavior can be described with the formula where the new y is 2 times the value of the wall minus the y that the bacterium was supposed to get, which is outside the box. The same formula also goes for x, of course. So now we know this formula, we can implement this in our logic flow. Since we are going to keep the simulation running until the bacterium escapes out of the box, we do not have any time constraints anymore. So we can say, well, time is smaller than infinity, which is always the case. This does mean that later in the code, we will need to apply a rule that will make the loop stop without adding the time constraint. The first part of our code doesn't change. First, we have to define our variables and calculate the new x and y. Once we have the new position on x or y, we have to define whether this position is outside the box or inside the box. And if it's outside the box, we have to correct for that. We can check whether the bacterium is outside the box using if statements. Since the logic flow behind this isn't that easy, we can best completely write it out. First, we have to check whether the y-coordinate of the bacterium is in the box. If this is true, we should move on to check whether the x-coordinate of the bacterium is in the box. If this is also true, it means that the new position of the bacterium is within the box and we don't need to correct its position, so we can just plot this new path. However, when y is not within the box, 2 new possibilities arise. There are 2 limits for y, so we have to consult both options separately. Then, when we find out which border the bacterium has passed, we have to correct for it. If the x-coordinate is not within the box, we have even more options. since it could be outside the first wall, it could be outside the second wall, or it could be within the gap. If the bacterium is outside one of either walls, we have to correct for it. If the bacterium is outside the gap, we should stop the loop. However, this flow is not finished yet, because it's also very well possible that the bacterium ends up somewhere outside the box in the corner, so both outside X and Y. This means that we again have to define all the possibilities for X under the possibilities for Y. This system now becomes annoyingly hard to define, because if we count the amount of if statements we would need for this big block, we would need around 11 if statements, and that's a lot of work for a program that is supposed to make your life easier. So we need to define it a little bit differently. Even though it's nice to define everything in one go, it's not always the most elegant solution. We need to check both the X and the Y coordinate anyway, so let's just make two separate if blocks out of it. As you can see, this becomes much easier to define than the big chunk of logic flow we just wrote, and this is also much easier to put in MATLAB. So let's add these two if statements to our flow. First of all, we are going to check whether the new I coordinate is within the box. If this is not the case, then we have to correct this coordinate in such a way that it stays within the box, so it bounces back. And if it is the case, we move on to the next if block, where we ask whether X is in the box or not. If X is not in the box, there's two options. The first one is if it's in the gap. If this is not the case, then it's outside the wall, and we have to correct the X again, so it bounces back. Then we can plot this, and then we can repeat the whole loop again. However, if it's in the gap, we have to in some way stop the plot. We can do this using the break command of MATLAB. And then we have to plot the final position. And so let's put all of this in our code. Let's also keep the flow there to see what we have to do. The first thing is change the time span to infinity, since there's no more time limit. So the whole loop keeps running until we reach the breakpoint where the bacterium escapes out of the gap. Let's also move the time calculation a bit up then. So now we can add the if statements to our code. First we were going to check whether the bacterium passed the wall at the Y coordinate. So if the bacterium passed the first wall, and then we have to correct for it with the formula we got in the exercise. Then we can check whether the bacterium passed the second wall. And if this is the case, we again have to correct for it. And that's actually all we have to ask for Y, because all the other possibilities we will check in the if block for the X coordinate. So now we can define the if block for X. First we check the easiest part, whether X passed the first wall. And if this is the case, we have to correct for it. Then comes the more challenging part of the X block, which is checking if X passed the second wall. Because here there's two possibilities, which we define with a new if block. The first one is when the X coordinate is outside the gap. And this we can again define with Y coordinates of the gap. So if Y is larger than the gap or Y is smaller than the gap, then X is not in the gap, and we have to correct for this. And if this is not the case, then it means that the X coordinate is in the gap, and we have to stop the code. And this we can do using the break command of MATLAB. So let's go through it one more time. First, we define all our variables. Then we calculate the new X, Y, and T. Then we check whether the bacteria moved outside the walls at Y. Then we do the same for X. And then we check if the bacteria moved out of the gap. If this is the case, we break. If this is not the case, we move on to plotting. However, we should take into account that when it breaks, it does not plot the last path. So let's also add that before the break. Now it plots everything. This whole loop keeps repeating itself until we find that the bacterium is in the gap, because then we break from the loop and we plot the final position. We only need the title where we state how much time it took for the bacterium to escape. We can make a vector, and in this vector put the string t is, and then using the num2string command we can display the time as well. So let's run this because everything should be in place now. And indeed, we see that the bacterium does not escape the box anymore. It nicely stays within the borders. It took him around 3,500 seconds to escape. If we run it again, we get something different. Now it took almost 2,300 seconds and a whole different path. Now the bacterium was really fast, only 350 seconds. So this proves our code is working and that we can indeed simulate the escape of the bacterium in the from the box. So let's move to the third exercise. In the third exercise, we want to make a histogram of the escape times of 2,000 simulations of the bacterium escaping the box. So this means we have to perform the while loop we just constructed, then save the time, and repeat this for 2,000 times. We know how many simulations we want to run, 2,000, so we can use a for loop. This means we have to put a for loop to run our while loop 2,000 times, and then each loop store the t, so in the end you get a vector of every t of each simulation. And using this time vector, we can then plot a histogram of all the different escape times of the bacterium for all the simulations we did. Because we are going to run so many simulations, it's also best to turn off the plots in our code, because they take up a lot of computing power and we don't really need them. Let's add this to our code to solve exercise 3. First of all, we were going to define the for loop. We want the whole while loop to happen 2,000 times, so we build it around our while loop. So for what n is 1 to 2,000, and then close it with an end. So when we're in the for loop, we have to do the while loop. However, we don't have to change anything in there. We do have to turn off everything that we need for the plot, so let's do that. Using Control R, you can quickly insert a percentage sign that will turn a piece of code into a comment, and therefore it will not be active. So do that with all the plot commands. That will speed up your code a lot. Now we have done that, we can store the time. So let's store it in a vector we call time, and then just say the vector time is the old vector time with the new t behind it, just like we did in previous exercises. Also, don't forget to define the empty vector time at the very beginning, so MATLAB knows it as a variable. Now we have changed everything in the core of the code. We just have to plot the histogram. First, remove the final plot from the previous exercise, and instead type histogram time. This way, MATLAB will make a histogram of all the time values we have stored in the vector time. The output will be a figure, so we also have to define the x-axis and y-axis. On the x-axis, we see the different amount of times that occurred between all the simulations. On the y-axis, we will see the amount of occurrences of each time, which is typical for a histogram. And in the title, we can type what we see in the histogram, and that is the different escape times of the motility simulation we just made and the amount of occurrences of that. So when we run this, we get a nice histogram, and we see that there's quite some diversity in the escape times of the bacterium. It usually escapes fast, but one time it even escapes at a time of 2.5 times 10 to the power of 4 seconds. So that's a lot. We can run this again. So what we get now, we see that the division of the escape times is different. than the previous one, which proved that each simulation is indeed also different. Now you are able to model 2,000 bacteria that each go their own way, which brings you one step closer to modeling entire biological systems.